So, what if I told you that for decades, the way we kept airplanes from falling out of the sky was, well, based on a complete myth? That's really the story of reliability-centered maintenance. It's a philosophy that didn't just change aviation, it totally redefined our relationship with failure itself.
It's one of those questions, right? When should you fix something that isn't broken? Seems like it has a pretty obvious answer, but, for the early aviation industry, getting that answer wrong wasn't just some philosophical debate. It was literally a matter of life and death.
For years, the logic was super simple. Old parts break. That's it. But when engineers actually sat down and looked at the data from thousands and thousands of flights, they found something that completely defied common sense. And it forced them to, well, rewrite the entire book on how to keep planes safely in the air.
Okay, so let's really dive into this. It all starts with that idea we're all familiar with, right? Wear and tear. We all just kind of assume that the more you use something, the more worn out it gets and the closer it is to failing. It just feels right. It's common sense. And this led to what you could call the brute force approach to maintenance. I mean, just picture it. Mechanics tearing down perfectly good engines just because a calendar on the wall said it was time. It was incredibly expensive, super inefficient, and as it turns out, a lot of the time, it was completely pointless. And here is the absolute bombshell. When the engineers crunched the numbers, that nice, neat, predictable wear-out curve they expected to see, it just wasn't there. For most of the really complex parts of an airplane, failure was a total game of chance, not some predictable function of age. Just think about that for a second. The very process that was designed to prevent disasters was, in some cases, actually making them more likely by introducing human error during all these unnecessary overhauls. It was a truly terrifying realization, and it sparked a revolution in how we think about safety. This quote from a 1960 United Airlines report just perfectly captures this new way of thinking. It wasn't just about how old a part was anymore. It was about this chaotic, unpredictable dance between all the different stresses and a part's ability to resist them. The old simple rules just didn't apply in this complex new world.
And so, this brings us to reliability-centered maintenance, or RCM. The huge idea here: stop focusing on the individual parts and start focusing on the function. So instead of asking how old is this thing, RCM asks what does this thing actually do and what happens if it stops doing it. This right here is the heart of RCM, and it's a total game changer. It's the shift from trying to look into a crystal ball to doing a real risk assessment. Because in the end, it's not about trying to predict the future, it's about managing the consequences. So how does RCM actually do this? Well, you can think of it like an emergency room for machines. Every potential failure gets triaged into one of four categories, which range from, a minor scrape to a full-blown, life-threatening event. Top of the list, of course, is safety. This is anything that could put the aircraft or its passengers in immediate danger. We're talking an engine exploding mid-flight. For these kinds of potential failures, the goal is prevention, pure and simple. Then we get to the money. An operational failure, that's a major headache. That's the broken part that gets your flight canceled and leaves you stranded at the airport. A non-operational failure is way less dramatic. It's just a part that gets quietly fixed overnight, and you never even knew it was broken. And now we get to the scariest category of all, the hidden failures. These are the ticking time bombs, the silent assassins of the system. They're the broken parts that don't cause a problem by themselves until something else breaks. And that's when things get really, really dangerous. So how do you fight an enemy you can't even see? Well, let's look at a real-world example that shows just how clever and how absolutely crucial RCM can be. So, deep inside the guts of a DC-10's air conditioning system, there's this tiny, unassuming part, a bulkhead check valve. It's a classic example of a hidden hero, or potentially a hidden villain. This little valve has one job: to be the last line of defense against a sudden, catastrophic depressurization. If it fails, you would never, ever know. But if a duct happens to rupture after that valve has already failed, well, that's when you have a recipe for absolute disaster. And this is the magic of redundancy. The odds of one thing failing might be pretty high, but the odds of two independent things failing at the exact same time, they're astronomically low. RCM's mission is to keep it that way by hunting down those hidden failures before they can find a partner in crime. So what happens when you take this consequence-driven logic and apply it across an entire aircraft, from the engines all the way to the landing gear? The result is a maintenance plan that looks a lot less like a simple to-do list and more like a complex game of chess. Take this DC-10 brake assembly. RCM doesn't just see a part with an expiration date. It sees a complex system with a dozen different ways it can fail, and each one has its own unique set of consequences.
And this is what that looks like in practice. If the brakes are wearing down, okay, that's an operational issue, so the solution is a quick visual check. But if a pressure line is leaking, that's a hidden failure, so the mechanics actually have to go hunting for it. Every single problem gets its own custom-made solution.
So, in the end, RCM is so much more than just a maintenance program. It's a whole new way of thinking about risk, one that has made flying safer than it has ever been. And it's the answer to that tricky question we started with. When should you fix something that isn't broken? The answer, it turns out, is, well, it depends. RCM completely revolutionized the skies, but its real legacy might actually be right here on the ground. From our hospitals to our power grids, we're surrounded by these incredibly complex systems that are on the brink of failure. So what if we stopped waiting for them to break and started asking the right questions?